Hello, my name is Ethan Noor, and this is my presentation about what I've been working on with Dr. Oyen in her lab. We have been developing biomimetic hydroxyapatite hydrogel composites that can be used for bone tissue engineering. For some background, bone tissue is made up of hydroxyapatite, a calcium phosphate mineral, and is set within a collagenous matrix. This hydroxyapatite can be formed utilizing an alternate soaking process. Combining this process with hydrogels gives us the ability to create extremely biocompatible hydroxyapatite composites that allow the mineral to subside in the natural gel matrix. This process can be formed on many different scaffolds, including 3D printed surfaces and glass slides. The figures on the top row show 3 different composites developed on different scaffolds. The one on the left is a pure hydroxyapatite coating on a 3D printed scaffold. The one in the middle is an agar hydroxyapatite composite on a glass slide, and the one on the right is an alginate hydroxyapatite composite on a glass slide. The left 2 figures were made utilizing the alternate soaking process, and the alginate composite was made using the alternate spraying process. For the materials and methods used in this project, the alternate soaking process was where it all started. This dips the scaffold into calcium and phosphate solutions for a minute and then alternately dips them in distilled water for a 15-second rinse. To automate this process, a Lego robotic crane was constructed and programmed to dip the scaffolds at the right time for multiple rounds. For thin samples, roughly 25 dips were used. For bulk samples, that increased to about 100 dips. The figure in the middle shows a general schematic of the setup I was using. The solutions shown used in the alternate soaking process can also be put into spray bottles and be nebulized onto the scaffold. This method was effective and allowed for more bulk samples to be produced quicker. The dispersion of the solutions on the scaffold from spraying allowed for a more even coat all around. For the results, I was able to successfully create hydroxyapatite gel composites from gelatin, agar, and alginate hydrogels. The alternate soaking process was very successful in creating good, strong, biomimetic hydroxyapatite agar composites. The alternate spraying process was very successful in creating hydroxyapatite alginate gels, especially because the calcium could be isolated and used as not only a part of the mineralization of hydroxyapatite, but also in the cross-linking of the alginate gels. Alginate gels differ from other hydrogels in that they are a polysaccharide chain that need an ionic cross-linker to gelatinate. As you can see in the photo in the bottom middle, it shows the process of the calcium cation cross-linking the polysaccharide chain. Below that shows a freshly sprayed hydroxyapatite alginate sample after the cross-linking and mineralization has occurred. To the right of that shows the FTIR characterization of the hydroxyapatite coating formed from the alternate soaking process. As you can see from the spectra, there is clear hydroxyl and phosphate peaks shown. Calcium does not show up on FTIR, which explains its absence from the spectra. Some applications of the work that I have been doing can be found all over the biomedical industry. We have attempted to use the alternate soaking process with a tooth mold, and the results can be seen in the figure in the bottom left. It worked decently well and shows that this is an efficient process to create a strong, biocompatible hydroxyapatite hydrogel composite that can be used for bone tissue engineering in the future.